Welcome to today's research seminar. We are happy to have Peter Egger here, who has done a lot of work on international economics and regional economics, and he's working at the ETH Zürich. And yeah, today he will tell us a bit more how uncertainty shapes a spatial economy.
Thank you. Thanks a lot for having me. I'm very happy to be back for this seminar, and apologies to everybody, including Gabriel, who has seen a version of this talk already. I'm presenting former work with former student Katharina, who is now at Düsseldorf, and a former postdoc who is at Paris School of Economics now. How uncertainty shapes the spatial economy. So uncertainty is clearly at the heart of this paper. And basically what we want to tackle is the following problem. If you have forward-looking agents that make decisions today that are influenced by their conjectures about the future, and the future has big uncertainty. The question is, how can they make optimal planning decisions about the future when these planning decisions depend on other agents? So this is a complicated problem. And what typically people do is they make simplifying assumptions by way of time being continuous. This is very key. If time is continuous, it basically means that tomorrow and today are identical. Right? But if time is discrete, tomorrow is discretely far away from today, and that generates a gap between things that influence me today but are in the future. When you have continuous time, future and present is identical. So the problem is that our data in economics, they come in discrete time gaps usually, and very often we work with long interval data even. So that's a problem. And then also the decisions that we make are also in non-continuous states, like what is the textile sector versus food versus machinery. These are even unordered in a way, unless you're a crazy input-output person and do an inverse, Leontief inverse, and rank things by upstream as or downstream as, then they may be ordered. But other than that, I have no way in thinking of sectors as being ordered. And also Linz and Vienna and Innsbruck and Paris, these things are discretely far away. So when you are fired and you have to look for a job, in particular when you're a manager of a company, right? Typically the next job is far away. So what happens when everybody in textiles is under pressure? Now Lansing, we read in the news, has problems and is about to fire 600 people. So what if those are specialists and the next company or the next city where such an agglomeration of demanding certain jobs is located is far away? That's the problem. Basically, we want to talk about something that is discrete in space and discrete in time, where people make forward-looking decisions that are influenced by what other people are doing. And all these things are discretely far away, and the shocks we are facing are big. So that's basically our thing. We want the car manufacturing sector, textiles, we don't want them, but we want to consider a situation where these things are shocked big time, right? Like AI, everybody is talking about AI. How is AI going to affect us? Eventually, all brain surgery is going to be handed over to computers in a while, and then what are all these brain surgeons doing, right? So that's basically the problem. So to put this into motivation, we know that when you're a trade economist, you're concerned a lot with welfare analysis, right? You're computing welfare gains from trade liberalization. The EU, what did it do to the enlargement countries, to the incumbent countries, etc., in general equilibrium? And on average, we compute that there are gains from liberalization, and this is all nice, but then there is a big literature saying, well, even though the average long-term gains are positive, there are gains, there is a big distribution around these gains, and there is losers and winners, right? And so for that reason, there is opposition against liberalization at times. There's winners and losers, and the winners, it takes a long time until the gains are materializing. So it can be that I remember when I was a kid or a teenager that there was Opal hit by a bad shock, and basically a whole city was getting unemployed. I'm exaggerating, but you can imagine with coal mining in Germany, etc., there is regions where a large chunk of the labor force is set to unemployment, and people have to escape that. And what we see in the data is that people are really trapped in situations. They don't escape in the way we think or we assume they will in models. They are staying unemployed rather than moving to the next place where they can find a job eventually in another sector in another city. So there is this trapping, and Rafael Dix-Canero had a bunch of papers on this and the different assumptions. So this trapping is important, significant. It takes 30 years, a generation's time, for gains from liberalization to materialize. And this is documented throughout the literature. Adrian Bilal and Rossi Hansberg have papers on this, Rafael Dix-Canero, several papers, depending on what are other factors doing, how easy is it to adjust the capital stock and other factors of production. And jointly with labor, this matters as well. But, there's long time windows within which supposed gains from liberalization cannot materialize due to trapping and sluggishness and adjustment costs. Okay. Uncertainty is alleged to be one source for these gains not materializing in the short run, right? Because people plan ahead, and you're hit by a bad shock, and this is bad for you. But the question is, when moving to another city, you could say, well, I'm going to be a doctor there. But most people think, well, what if it's getting worse than it is now? So this is one reason for why people don't escape. There is a lot of pain coming from mobility costs, search costs, etc. You read about jobs, but the question is, can you get one of those? So uncertainty about this is a big factor. And in particular, in the macro literature, Nick Bloom and other people have documented that uncertainty itself is a cost factor that's not insignificant, in the range of 2-point-something percentage points of real income. That is important when compared to other shocks that we tend to analyze in the trade literature, like the China shock and other things, right? This is relatively significant, just uncertainty alone. So we might also say, well, if trapping is an issue and basically you have a finite lifetime and are thinking about whether to escape or not, of course, it makes a difference when you're young, when you have a whole work life in front of you, versus when you're old and only 2 years are left. Are you willing, with remaining 2 years, to give up your home place, to move to another city, to move to another sector? Will you actually be offered a job that requires retraining in another sector, etc.? So age might be a factor in that as well. Okay, just to put this in perspective, in one particular sector, the Bureau of Labor Statistics, you might say the specialists on this issue, they are doing forecasts for the labor force across different sectors for the US, looking 10 years ahead. And now imagine that you're in the textile sector, you somehow find the love of your life, you settle down in a city, you get trained as a textile worker, and you do this in the early 80s here, a time when the Bureau of Labor Statistics forecasted for you that, there's going to be job growth in this sector, 3.7% at the time. Now you got trained and you're basically locked in, you might say, in that sector because you're a specialist in textiles, whatever. Only 10 years later, everything plummets. This is basically China emerges in the market, right, and destroys textiles jobs big time. I once was on a plane with somebody from Northern Ireland. He said that basically all textiles jobs are gone except for his, because they're doing like bulletproof shirts, right? Now, if you live in the US, that's something really to think about. Not here, but for the military, etc. So those specialized things, they remain, but broadly speaking, textiles moved abroad. Right? And that was about that time, and later on, things were not as dire anymore, but still not rosy. Right? That sector is still contracting. So you can say, well, if me, as somebody who chose the textile sector, as somebody young, when the specialists in the labor forecasting basically said everything is going to grow, only 10 years later things plummet. You can imagine this is something that's real for people. Right? And it's the same for companies, right? There's a sector where things grow and only 10 years later, new technology, right? You're getting trained as a truck driver. Now it's probably not a good idea because I assume that 10 years later, there might be automated driving.
And these are predictions and the real data is probably even worse. No?
Yes, I agree. Yes. Yeah. Okay. So what we want to do, we want to think about uncertainty that is big in macro, basically, for people who think about asset allocation. Right? They think about, shall I put my money into savings? Shall I invest in housing? Shall I invest in cars in the stock market? And which type of asset? That's what people in macro are analyzing a lot in continuous time models, steady state, etc. We don't want to do all that. As said before, we want to deviate from continuity in every regard. Space, and when I say space, I really mean the cross-section. Be it a job, be it an education, be it education, be it occupation, be it a sector, be it a region, that's for me space. And then time, right? Because tomorrow is not infinitely close to today and it's not the same as today. It's a modeling trick to make tomorrow the same as today, because that gives you properties that later on I will briefly talk about. But that's not what we want to do. We want to say, okay, my data, they come at an annual, at a monthly level. And on the computer, when you're simulating things, there's going to be discreteness anyway all the time. So the question is, when you have this discreteness, how can we show certain properties? How can we prove contraction to an equilibrium, etc.? That's exactly what this paper is about. We want to give an algorithm for this problem. You have big uncertainty, a large shock, and then people have to optimize in discrete time, forward-looking, being unsure about the future. You can imagine how hard the problem is. I'm making a decision about tomorrow. I have a forecast, but I know tomorrow is going to depend on what everybody else is doing. And what everybody else is doing is depending on tomorrow. And tomorrow, it's again tomorrow. So that's the infinite future that matters here. That's computationally, you can imagine, hard to implement. But exactly for that, we want to design something.
But you assume that agents make those calculations.
Yes,
With full rationality.
Yes, and you could of course make other more let's say have a model of limited myopia, like Mankiw does these models where you look 3 periods ahead, which again is not implausible at all. Right? I mean, do I plan until my last moment in life? No. Anyway, people here don't look into infinity because they are finitely lived. But still, how far ahead do you plan? That's a separate question. But in any case, that's going to be a hard problem with big shocks and discrete time and discrete space. Right? And for that, we want to design an algorithm which, to the best of my knowledge, doesn't exist right now.
And people have to internalize GE.
Yes. Okay. To be honest with you, this thing has 2 components. One is the dynamic component, and one is the GE. The GE is really where we don't innovate. Right? In the general equilibrium model, we have an input-output structure between regions and sectors that's strictly Caliendo, Caliendo-Paro, and Caliendo and co-authors later on. So it's a simple I/O within time general equilibrium structure where firms in sectors use inputs from all the other sectors. There is prices, when I say prices, factor prices determined within time. So the innovation here is really about this part, because I could give you a factor price vector up until infinity in the future, and still you won't be able to solve the dynamic optimization problem of people settling in discrete time and discrete space right now. Because I give you the factor prices, but then the shocks, what do they do in determining total output prices? And how do I locate and where? That still is this problem where tomorrow depends on after tomorrow, et cetera, et cetera, et cetera. That's hard to solve, right? So that's where the innovation is really. We're going to do this with people looking into the future. And we're going to have, if you like, a Mickey Mouse condensed overlapping generations version that you could make a more realistic version. We don't do that for computational reasons, merely. And when I say computational reasons, I mean for data reasons. Because you will see that we're going to have in the implementation of this French regions, which you might say are fairly meso or macro regions in France. And then we're going to have sectors that are still fairly meso macro sectors. But the interaction between those and 2 skill levels only is going to give you an enormous matrix whose cells you don't want to be flooded with zeros. So that if you make this overly sparse, it's like you make an input-output matrix at the, we talked about it before, at the 10-digit by 10-digit level, say, that of course you will see tons and tons and tons of zeros where one product is not used directly in the production of another product, etc. So that becomes hard to tame, and people in physics would say, well, let's aggregate that with Brownian processes, we're going to get non-zero cells. So in a way, that's the basic reason why we keep things at a relatively aggregate level. But we have that, and then we have people of different age in this Mickey Mouse overlapping generations model. Newborn, basically lump of flesh, if you will, that are born to parents in a place, and the place is a sector occupation a region, and then they start making decisions moving into their first job. And it might be that, you know, if you're born to a pair of doctors, then the chance that you become a doctor is higher, etc. So that's all in there. And then you're young and earn money and consume, and then you get older and still earn money and consume, but then at some point you die and you're off the map. Okay. So that's the basic framework. So we're gonna model France with this. We have data on transitions between these regions, sectors, and occupations, as we call them, which is education, basically, high skill, low skill. And we find that there is actually significant reallocation of people when shocking the model just with uncertainty. This is not going to be a paper where I can tell you anything exciting about estimation, but we're going to use data on output, input, output tables, etc., to calibrate productivity at the sector region level, use a panel data set of that and estimate the variance for each sector region pair from data over time. Where say you have a simple autoregressive forecasting model just to get a metric of uncertainty. And what you can document is that this metric of variance around the forecast path is very heterogeneous across regions and sectors. And that we take as a metric. You can also use trade costs. You could say, okay, let's look at Trump, who and basically do a forecast about tariffs from past times here, tariffs, and now comes Trump, and boom, you get a big shock. So let's take that as the variance. You can have other metrics too. This is just to inform the model to show that if we eliminate that uncertainty, which basically means living in a perfect forecast world, perfect foresight, what is the equilibrium allocation of people that don't like uncertainty, looking like in the future in the steady state relative to nowadays? That gives us a metric of how important uncertainty is in making people doing these choices about where to locate in regions, sectors, and skill levels, etc. Okay, and what we document is that this is the level of uncertainty that we measure in the model does big time impact on allocation of people. Okay, so what we relate to, tons of static trade and regional models that basically determine prices and eventually allocation of people across, say, jobs or regions and sectors. Then there is dynamic models. Artuch, McLaren had a number of papers with co-authors. Lorenzo Caliendo and Fernando Parro had a bunch of papers. Treb Allen and Dave Donaldson, Rafael Dix-Canero has several papers that relate to us, which are dynamic, under perfect foresight, or under imperfect foresight, but approximately linearized around the perfect foresight steady state or some other path that is basically perfect foresight. In the macro literature, there's these so-called Hank models, heterogeneous agent new Keynesian models, where basically people think of, you know, when there is uncertainty, how do shocks lead to reallocation of assets between different classes of assets, savings, and whatever. Continuous time, everything else continuity, no spatial dimension other than these asset classes. And then there's two papers that basically, three papers. Bilal has a paper on the master equation, which relate to all continuity, right? All continuous time, continuous space. So in that sense, yes, in terms of interest related, but in terms of technology, completely unrelated to what we're doing. Okay. Okay. So here is basically the ballet of what happens in the literature on uncertainty right now. So state the problem in continuous time, irrespective of whether there is known factor prices or not. In the macro literature, that means known interest path into the future or not. The interest rate is not determined. It's not an object of interest. It's just there. Question is, how do people reallocate their assets between classes of assets? Compute the steady state of the model and note that steady state in principle could exist, but in a non-stationary model, it might not, right? I mean, and we have something to add to that literature too. But typically you have a steady state linearized around the steady state in 99.99% of the cases linearly, so literally linearized or approximate higher order. And nobody talks about this, but this is big time difference in terms of computation, right? This is not just going one order higher. We talk about days of convergence versus seconds, right? I mean, this is how big that difference is. And use projection methods to reduce the dimensionality of the problem and solve for impulse responses by eigenvalue decomposition. That's Steve Redding and team. Master equation of the linearized continuous mean field game, continuous meaning continuous time, continuous space. Adrien Bilal, used by him and Esteban Rossi-Hansberg as well. And then perturbation not around the steady state, but around the path, which is the perfect foresight path, linearize around that. What all of that requires is that the basin of attraction, so basically the gap to the steady state level or the gap to the path is small. Because if it's big, who tells you whether you're going to converge there? Nobody knows, right? And that's exactly something that we don't feel comfortable about, because what people like to do these days is, right, they try to put a lot of water on this planet due to global warming and coastal regions disappearing and all sorts of gigantic shocks. And, you know, what's done in these models is not designed for big shocks. It's designed for marginal deviations from where we are, right? But nobody's interested in marginal here. So what we want to do is something completely different. We want to have the discrete nature, nonlinearity of the model, out of steady state dynamics, tractability of uncertainty of the aggregate type. So everybody has individual uncertainty in the sense that there is people heterogeneity and we don't observe it. Somebody loves to clean toilets. So for some reason they don't move to a management position. They just love doing that job. That's a vehicle in that literature to make sure that there is somebody in every job, right? That's there anyway. I call this micro uncertainty because that's the individual idiosyncratic, and I'm getting a draw tomorrow. Today, people move, right? There's always movers between different types of jobs, regions, sectors, etc. That's micro. I'm not interested in that. I'm interested in aggregate uncertainty, meaning there is a big shock happening to textiles or textiles in a village to one big company that's a big employer. That's what I'm interested in, because that's where the beef is. I think that's what we are talking about when talking about climate change, etc. So we want to state the problem in discrete space and time, compute a finite difference approximation of the full nonlinear model. That's different from a linearization or second order linearization, because as you will see, we're going to take a nonlinear function that has wide distribution eventually and put a grid on it and linearize between these grid points to take care of the whole full nonlinear distribution. It's like when you work with approximations, Gauss-Vermeide quadrature of multivariate probability distribution. Also, you put a grid there, and then you integrate over this. But you integrate over the real function, the nonlinear function, rather than linearizing, right? That's something conceptually very different. Write the model as a coupled mean field game and do piecewise linear interpolation of the master equation. Okay, so here's the model. Time is discrete.
So Peter, in
Yes.
the discrete version, you have a coordination product. No?
Yes.
But you don't have any continuous.
Exactly. Yes.
And so the tool to solve the coordination game is the mean field game.
It's the mean field game with a trick that we do, that is this piecewise linear interpolation, where we construct theory consistent barycentric weights through which we pass all the individuals. And then we do this interpolation of the stochastic function. It's the uncertainty. Basically, you draw a shock from a distribution. And then all the people may end up in Vienna or in Mödling or wherever, right? So there's distributions of people across jobs, sectors, education levels, regions, etc. And over that, this is like doing a linear approximation of this high-dimensional distribution function. We put grid points there, we interpolate, and we get the whole set and have an exposed test strategy that we prove as well is valid to tell you whether the alleged equilibrium distribution of people will be inside of this, you might say, ellipsoid of points in this high-dimensional distribution. Okay, so good. Model time from 0 to infinity. Now I'm going to use the word job a lot. I already did. And job is basically a triplet of things. I'm calling a job region, sector, skill level. I'm calling it occupation here because it could be more than just skills. I didn't want to blow this problem up to be a too big a state space because of this empty cell problem you will see in a second. Okay, so this is a job, but regions, sectors, skill levels are a job, and then I will have a shock that is basically region sector level. Think of it as follows. There is a textile shock, a textile sector shock that would only be S specific, only be sector specific. Or there is a particular lensing, right, which is hit in Vöcklabruck, I don't know, that's a region sector job, shock, right? But the job is region sector occupation. So that means that the shock is marginal, right? It hits a large segment of the labor force in this space. Now, in the cross-sectional GE model, as said, I don't have anything interesting to say. We quote quorum caliendo paro. It's basically a caliendo paro economy input-output model for the French economy, about 20 regions. I don't remember, 20 regions, say 20 regions, 20 sectors, not accurate, but something like that. 20 times 20 is like 400. Then you have this is not enough, but I'm just giving an example. 20 regions, 20 sectors, 400 pairs. And 2 occupations would be 800, right? You can imagine from any one of those states you can be today and then tomorrow. That's 800 by 800. It's already a big matrix with many cells. The more fine-grained you make the regions and the sectors and the occupations, the, of course, larger is that vector and the bigger is the matrix, and the more likely you will have zeros in that cell, right? I mean, if you say Arsenal 20, who I don't know, with a university degree in physics is going to move from that space to I don't know, Vöcklabruck in the same sector. I mean, how many are doing that? 0, right? I mean, you can imagine if you make this too fine-grained, there's a lot of sparseness, and we don't do that. But we're going to be fairly fine-grained. Then there is an input-output structure. So all sectors and regions are buying from all sectors and regions, potentially. And then wages and other labor market prices, factor market prices are determined, like we have a capital sector, housing sector, etc. Not interesting. That helps us to back out on sales data at the region sector level productivity, right? And that's going to be the metric on which we are going to lean with panel data across regions, sectors, and time. Right? We're going to forecast that but with an AR1 model, basically, and say, okay, the deviations from that trend we take as a metric of uncertainty, and then we take this, right? And we say, okay, and now let's shut it down and see in a model where people have either perfect foresight and there is no shocks, or imperfect foresight and there are these uncertain shocks, how will the steady state allocation of people and real consumption look like in these models, okay? So, people make choices about jobs in the next period. We have this quadruple-pronged age structure. You're born somewhere, I said. I mean, we don't have forward planning parents. These parents here are not benevolent. They don't want to dump a child in a good place. Children just happen on the way, right? They only consume. They don't receive utility from children. They have them. You could make this a fertility model too, which we don't. But right now, children just happen in order to have an ergodic, to have a constant size of the labor force for France later on. So once people are born, they're just sitting there where their parents are, and now they make decisions of where to go tomorrow. And there is mobility costs of staying in the same job and region as their parents, and other ones of moving to another region and sector as their parents. We can estimate that when you're newborn, you become young. Right? And nobody's dying as newborn here. We're good in that regard. But then we want to keep the age structure ergodic in France. So we want to make sure that the fraction of people who are young and who are old is always the same. We can do that by basically having a probability of transiting from the young state in which you're, I don't know, 20 years or so for your lifetime until you become old. So everybody who is young has a probability that makes sure that there's always a constant number of people being young. And there is a constant number of people being old, and there is a probability of staying young, becoming old, staying old, and dying in the model. And the dead and the newborn don't consume, right? And just the newborns sit there and the dead are gone. Okay. So at the end of any period, the household draws again and again a taste. Right? And the taste basically makes them, given things that are common across the people, like mobility costs and wages, etc., makes them still leave. You know, you find the love of your life and you move, boom, to Innsbruck tomorrow. That can happen, and that's due to this epsilon here, which we draw as is customary in the literature from a Gumbel distribution. That just makes sure, you know, that there is a good proportion between the tails of the distribution, so that there are enough people in every job, but not too many in odd jobs, etc., so that the attraction of high wages, etc., is not overturned. Then we have mobility costs, which we here portray as heterogeneous between the age groups. Forget about that. Basically, just ignore that. There's mobility costs between jobs, where the origin job is J and the new job is N. That structure is only there to not overcome the fact that when you're old, the future lifetime income that you have is shorter, right? So when somebody offers you a high wage, you also know moving to a new job means mobility costs. So even if they make you a good offer, that you have to counterbalance with the mobility costs with the high wage, you have to counterbalance. So the old are less likely moving, as we see in the data, and that's just there to make sure that is the case. So here is already part of this one important element here. This is the Bellman equation from the perspective of an individual, right? So basically what you have here on the left-hand side is the value of somebody H at time t being in the age class A. That could be newborn, that could be young, that could be old. Of course, for that, we don't write it. And in the job J, what is that? Well, that is the utility, and utility here is basically just a log utility about consumption, right? As you have in every trade model. So if you have a standard Eaton quotum or whatever model, forget about all that right thing here. So the only thing that the real value for you, you feel attracted by is basically real income. How much can you consume, right? Here, consumption matters, of course. That's what you have today from a good job. But then there is also every job. I always say when people ask me what's so good about Zurich, I say, it's great to get away from, right? The airport is so close, a short tram ride and boom, you're in the world, right? Cool. That's this thing here. The opportunities that you have from being somewhere of getting better, moving on to the next phase, to the next base. What matters for that? Well, across all the future options that you can take, staying, going to another job, etc., the draw that you get, you know, some people are crazy about Donauin's, a lot of people are crazy about the beach, the sea beach, right? That's all in that. I cannot explain it. We needed to see people move around in all these places. Mobility costs, which are not time indexed, right? When you're in textiles today, again, going into chemical industry is expensive. When living in Vienna today, going to the hinterland of Linz is expensive, right? For somehow, or the other way around too. So there's mobility costs. And here is the present discounted value of the future. It's very important. So here you have a discount factor, and that expectation basically depends on two terms. And these, it's two because of these two generations that we have. If you had like a 40 generation model, then you'd have 40 terms here that basically tell you, okay, tomorrow I'm going to be, I don't know, 31, 32, 33, etc. For every age, you'd have a separate term here. Here we just have the probability weighted being in your present age group versus moving on to the next one, right? And the big V, that's very important, is the average value that you expect from being in a certain place, right? Here, this here is idiosyncratic. This is just me, but where I'm going, the present discounted value depends on the average, and that's where other people matter as well. Yeah, I can't read that. Okay, so
can you say something about the stochastics you do over the expectation over the households?
So
and over T as well.
Yes, exactly. There is two expectations. It's very important, but thanks for pointing this out, Michael. One is across the households. That's the big V that comes basically from averaging across people, right? I'm saying, okay, tomorrow in that job, what I'm expecting is the average. And then, of course, I'm integrating over the future, and the future is differently long for somebody young versus somebody old versus somebody newborn. Okay, so there's indeed two different expectations happening.
It's stochastics comes from this factor productivity, random wages or something like that.
In the end, yes, random wages. Yes, the productivity, of course, materializes in everything in the cross-sectional equilibrium. It goes into all the factor prices and all the final goods prices. Final goods prices matter for, of course, how much can I afford, but also how much I earn for the current, etc. Current and future real income. Yes, but there is a second stochastic term, which is this Gumbel term, my idiosyncratic problem. Okay, which I unquote. So now writing that thing for the average is very important, because the only thing that is really individual here is this epsilon. Only how much I like one job over the other, one region over the other. It's just idiosyncratic. I don't know, you are born somewhere and you like things better than other people. I don't know. Okay, now I'm averaging this, and you can see here's now an expectation coming, because that thing here is going to be averaged out with the Gumbel. Later on, I will do that. Still, this is basically everything the same as before, just a little reshuffling, the expectation happening here. Yes, please.
Could you explain quickly these different conditional expectations? You have conditional expectation relative to time t, and then what is this h here on the left?
This is the individuals. This is all the people of my type that are relevant for me, basically, because what you guys are doing will matter for the price vector in the future, right? So if I know that everybody's going to move to Vienna, I know housing prices are going to be high in Vienna, wages are probably going to be high in low in Vienna, because there's so much labor supply there, etc. So that's where the across people aggregation matters, and this is the across time, because I'm looking into the future. Okay? This is what makes it actually hard. Okay, so this is the Bellman equation for the average individual of a type, and the type is age class and being in a job, right, at time t. Now, we need two more conditions. One is what I call the policy. What can you do if a bad shock happens? Well, you move, right? And the policy basically describes what for the average movers is going to happen. And clearly here, this nu here matters, which is basically this description of the Gumbel distribution. So what you need for this epsilon is actually a functional form of a distribution that is explicit, right? Because otherwise I cannot handle that. If that would be non-parametric, it would be horrible. So that's a parametric function, and often we use to Breschet these days, or to Pareto. Now, in the mobility literature, people use Gumbel a lot, but that 1 over nu here has the same role as the theta in Eaton-Cohen models. It governs the dispersion of these epsilons. It basically says, okay, how different are people in liking cleaning versus being a university professor, the WIFO president, right? So that's there, and that basically the policy here is a ratio. It integrates up over everybody, right? I mean, it sums up over all the options to 1. So everybody is going to do something, it's going to come from somewhere, and it's going to end up somewhere. That's that mobility here, and you can see that the basic structure is very much like what we saw today and yesterday in several talks. You have these, if you're a trade person, you have these job pair trade costs. This is not trade, this is flowing of people. So this is labor motion costs in a sense, age group and job pair specific, and the rest is basically telling you the value of a job on average, and it's composed of 2 terms only because of that structure. So you can say, okay, this is an old problem, a fixed effect that's origin specific, and a pairwise trade costs and things add up to 1. It's a logistic function, right? As you're used to.
But this can be negative, isn't it, in the denominator?
Denominator, well,
So if the theta is really, really big, then it's negative.
well, it's an exponential outside, right?
Oh, see, okay.
Okay, so
Then it's 0.
right, exactly. So it's just, of course, if the zeta is very high, it means mobility costs are very high. You're going to stay in a less good place, and the fraction of movers will be small. So I'm using that policy now together in basically that law of motion, which is called the Kolmogorov equation. It tells you people are here somewhere, okay? How are they going to transit into the vector of people being somewhere tomorrow? But that tells you, okay, the young tomorrow in a certain job are going to come from being young or come from being newborn, and with probabilities they weigh up. Same number of young people all over the place in France, but in different allocation, and the same thing for the old. That's the mobility equation. So we have the people who move that affect the wages and prices tomorrow, which of course are important in making my decisions of where to move, because if everybody moves to a place, then wages are going to go down, costs are going to go up, less attractive, etc. Okay, so these two things are really key. The Kolmogorov equation, determining the dynamic motion of people between places, and the Bellman equation, determining the vector of changes in value, in attractiveness, you might say, for a person of a type in a place. Okay, so
There's no sector index.
oh, there is sector, sure. So that's all in the job. The job is a region, sector, skill, right? Okay, so within period equilibrium, I said nothing special. That's Caliendo-Paro, the pins down vector prices, wages, we have structures costs, we have land costs, whatever. Dynamic equilibrium, that's where the beef is. And we say, okay, we have these J many jobs, we have the eta 2 H classes, and we have Z discretized configurations of stochastic shocks, bad, medium, low, right? Something like that. So that's going to be key, because what we will do is not solving, and you cannot, nobody can in this world, right? Nobody can, for any possible continuous bad or good shock, set that, solve that equilibrium model into the future. It's impossible, fundamentally impossible. What we're doing is this trick with this discretization of the stochastic space. Okay, so what things depend on is this aggregate endogenous state where people are, because they can move. And the aggregate stochastic state, this is basically these TFP shocks that people get. And these Z's, we're going to make, say, 5 points on the distribution of estimated variances of how good or bad technology shocks are. And we shrink those to have to be basically just a point versus a distribution in order to compare perfect foresight versus imperfect.
Sorry, in the steady state, there is movement around.
Yes, but ergodic. That's important. It's an ergodic distribution, ergodic.
Yeah.
So that there's individuals move all the time.
Move for the
fraction of people who stay. Yes, that's important. Yes, in the steady state. We could do this also for non-stationary, but in showing and other than that, cross sections just Caliendo-Paro. So what we can see, or what we can prove here, is basically we put big P many points around the stochastic, big P many points around the aggregate deterministic state. That's the L distribution. We basically say, imagine the following. We say in Vienna, there is going to be 0.1, 0.4, 0.5, 0.6, 0.9 fraction of all the people of Austria in a given job, right? I mean, that's of course absurd, but anyway, I can put such points, that's the P's. I fix those, right? And now I put Q many such points on the TFP shock, right? I have Q many points, say 5, P is 5 and Q is 5. 5 many points around, what's the proportion of people in that job? What's the proportion of shocks that are that big, etc. And if I'm doing that, I'm basically mimicking the continuous time situation, because what I can do now is I can say, okay, for that configuration of people, it's as if certain, right? I'm basically saying, okay, when solving the equilibrium for that configuration of distribution of people in space, right? Basically, it's as if I substitute for the Kolmogorov unknown equation, I get corresponding values for that distribution of people, and now I'm left with the Bellman equation in moving forward. This is not exactly how it works, but approximately that's the idea, right? To get rid of that, the future being discretely far away and unknown, I say, okay, let me remove that unknown thing with something that's known but has a lot of configurations that are possible. Right? And for all these configurations, I'm solving the model, and then I'm picking the optimal path forward. That's what we do. So that's the piecewise linear interpolation between these P many grid points of the distribution of people and the stochastic term. And we have a test whether we are in the equilibrium. So we have trapping here. I need to move on. Stylized model of calibration. I'm running short again. So 2 regions, no age groups. So a job is a region here. There is the rest of the world where nobody moves. The rest of the world is just with trade, pinning down, helping to pin down wages. People can move between 2 regions. Let me model it. That's our Eaton Quorum model with 1 sector only, and no interest in this configuration. So here's basically what we do. We have an AR1 process on the autoregressive process with region fixed effects here and whatever. We're estimating the error term. We assume that this is a normal distribution, etc. So what we're doing is having 2 regions that are totally identical, and I'm shocking them with high uncertainty and low uncertainty, but identical, right? So both of them get high uncertainty. So of course, when Vienna and I don't know, Graz get high uncertainty, there is absolutely no systematic incentive of people to move between Vienna and Graz because nothing relatively has changed between those. Yes, people don't like uncertainty, right? They hate it because they are risk averse. They don't like being punished by not knowing what the future is. But will they move? Absolutely not. 50-50 share as before of the population steady state because there is nothing, given everything else, symmetric, that the uncertainty does. Now I'm shocking people with asymmetric uncertainty and making region 1 actually less attractive because the volatility, the level of productivity is the same, but just the volatility of productivity changes. People dislike volatility. So what you see is that people move away. Right? With high uncertainty, the higher the uncertainty, the more people leave region 1 because they like certainty, even though that the expected TFP level is the same. They just don't like volatility. They go away, and volatility has costs, and then they react to that. Heterogeneous costs between regions. And here I'm doing the same for a 2 generations model, still no sectors, only regions, 2 generations, old and young. And what you see is consistent with what you'd expect. The young react more heavily because they have a double gain from moving, right? The future in which they get whipped is longer, right? The pain is stronger, and the moving costs are easier to finance because the future vector of incomes that they have easily accommodates those.
Very small effects. Huh? Very small the effects.
Yeah, but that's a meaningless model. It's just, it's just calibrate 2 regions and there's no quantitative meaning. It's just showing the qualitative effects. But yes, here the effects are small.
Is the role of the Markovian, say, characteristics of the shocks? So, if it is autocorrelated over time, I know if there's a shock now, the next one is similar.
Yeah, but we don't consider that. So right now the shocks are IID. You could consider even spatial. We have not done that.
The transition is Markovian, you said.
The transition, which transition is Markovian? Okay, we regress log TFP today on yesterday's log TFP,
yeah.
But the error, the epsilon there is
there's some persistence in it.
Yes, with a parameter rho. Oh, sorry. What did we put the rho on?
Up there, the rho.
But that's on the A, right? That's not on the on the epsilon.
The epsilon, yes, but
the epsilon is what the uncertainty.
Yeah, but the rho comes in, and that would mean it is somehow.
Yes. Is that exactly? That's why you see
that would mean it, today it's bad, tomorrow it's bad as well, but not that much.
Right.
Yeah.
So yeah, shocks have a memory. Yes.
Okay.
But not in epsilon, only in A.
And if it would be purely random, then would it be similar?
If it would be purely random, then we
wouldn't
see any movement.
Okay.
Yeah.
Then you would move. Okay.
Or you would immediately jump. You would immediately jump. Yeah. So if immediately the effect is a level effect, then you would immediately jump. Okay. So sluggish adjustment. Frames. How much? 0 is 0.
No, it's 1.
Okay. So we have 2,156 jobs to 22 regions, 49 sectors. It's a huge transition matrix, 2,000 by 2,000, right? Not many empty cells. We calibrate this model. We have labor shares. We have input-output structures. for this model. We estimate trade costs, we estimate mobility costs. So the mobility costs, so here's backing out TFP basically from a productivity equation where you can estimate these P over gamma parameters, and all the other parameters you can back out basically from the real sales. The TFP level, once you have this TFP level, you can estimate that model, which we actually modify in the ultimate paper. We have even agglomeration agglomeration effects. So more people moving to a place, higher productivity draws. That's not here. That gives you basically an idea of how big the distribution of these shocks is. This is the uncertainty parameter, the variance of the epsilon. So you see that there's a big difference. Some regions get big shocks, other ones get small shocks. And now we do a symmetric uncertainty where we say, okay, everybody from this epsilon distribution, we estimate one variance. Basically, we have one distribution and we put 5 points on that common distribution. And in the second one, we put region sector specific points on the distribution. And so this is asymmetric, we say, and we compare the two. Here, just a few metrics of TFP in manufacturing services levels. So there is heterogeneity. Here's mobility cost estimation. Distance between regions matters. Whether the sector is the same, whether the region is the same, whether the occupation is the same, interaction terms between those two, whatever we have from the data we use to estimate mobility costs. When calibrating that model, we can predict fairly well the stayers in the job. So most people stay from year to year in the job that they are, right? I mean, otherwise it would be absurd, right? Whom do you know who moves out of WIFO? Not so many people per year. So among the old, the fraction of stayers is larger than among the young, which is consistent with what I said before. Moving costs are heterogeneous between places in France as well. We calibrate the parameters such that the labor force stays the same. What's more important is we kill, so there is risk aversion, log utility. We kill uncertainty by basically making the distribution of epsilons degenerate. And what you see here, we have here the old and here the young, basically all jobs lined up in the same order. What you see is this is symmetric uncertainty. I don't want to talk about that. That's the asymmetric one that we think is relevant. What you see is a lot of people moving, right? I mean, you see this is 150% gains, 250, so there's more than 250% gains in some regions and jobs if you would remove the uncertainty. This is a big shock, even though we don't do anything. We don't do Trump, we don't do China shock, nothing. This is just removing the uncertainty from the data. So we want to say, well, uncertainty is something we shouldn't ignore, even though the values, not surprisingly, actually don't vary as much. That's not surprising because people move to accommodate big value differences, right? I mean, I'm moving away from places where the value shock is negative. That means the value shock for everybody staying in that job is going to be ultimately less negative because people escape that situation. But many, many people have to move in order for that to happen. And here we see that, there is sort of, when lining up incomes around these jobs, we see that there is a middle income class effect that's fairly big. And the percentage of the total workforce population that from one period to the next react to just removing uncertainty is 4.11%. That's not small. So here's the worst versus the best job. So there's always winners and losers. So what we say is, well, removing uncertainty in principle is something good for value. But of course, if you remove it from a place where uncertainty was very big ex ante and a place where it's small ex ante, the place where uncertainty ex ante was small, even removing it there may make that place suffer in the long run because it's a comparative advantage factor in the end of the day in a model where everybody's connected. So robustness not interesting. Thank you.
Thank you very much. You have still 5 minutes for questions. So you managed. Please, are there comments and questions?
Do you see any type of hedging instrument that's available to solve this uncertainty?
Yeah.
In this model?
Yes. So it's an interesting question. So Gianluca Durante asked me that question already once, so you're in a good part here. Yes, so in the end of the day, you could say, even though we don't have it here, you could use this as a policy informing tool in order for designing something like TA. So this trade assistance, this is not trade assistance, but something like an insurance policy that tells you where would we need to basically save as a government or subsidize a lot as a government in order to cushion this. Of course, I mean, the thing that you have to imagine is the signal of the market is a good one in a way. You might say, Christian Korsnick typically says that, well, if you make a lot of people move out of something, the market helps you to make these rational decisions. Of course, if you implement a policy that cushions the shock, you make people stay in bad situations. So you basically foster the trapping effect in a way, right? I mean, when you subsidize people in places where mining is killed, and give them subsidies in order to be better off without the mining jobs, you will generate unemployment in places where otherwise people would more strongly move out. But in the end of the day, of course, it can give you information which sectors, which regions will be most negatively affected, and then that could give you an idea as the government. I don't know, you could also finance these people for these people training programs to then go to other sectors, and from this model too, where the absorbing sectors and regions are, and you can incentivize people moving faster. So that's another way of using that idea. I don't know whether this answers your question.
What comes to me also is why will not everyone collapse into one region?
Yes.
Because if everything happens within one small region, you don't have this large amount of uncertainty until the mobility costs.
Yes, agreed that there's two reasons for that. Yes, you already mentioned one, mobility costs, and the second one is these idiosyncratic gamble shocks that lead to people staying in places even though all the economic incentives are there to move, right? The value is low, the mobility costs may be low, but still, for some reason, they like that place and they stay. So you might say that that's a modeling trick to some extent to make sure that you can explain the distribution of people, and seeing the wages and seeing the mobility costs. In absence of these epsilons, indeed, the distribution would become degenerate. Everybody would move to the best places. Right? But with this epsilon in place, everybody gets idiosyncratic shocks that leads to individual trapping in places at time periods. Tomorrow I'm getting another shock, but then somebody at the sudden fancies this place where I was. So there will always be that. We'll make sure that people are in all the places.
Somebody else has a question? Coming back to Thomas' first question, so I was wondering, in how far does maybe a high wage can be considered as a kind of hedging instrument? Because if you pay workers a wage high enough, then eventually they don't care about uncertainty anymore. And my second question is, in how far would the introduction of unemployment insurance in your model change the result? Because at the end of the day, unemployment insurance is, among other things, something to mitigate uncertainty, especially in terms of job loss.
No, I mean, yes. So let me answer the first one. The first one is very clear. I could numerically find out what up to a numeraire, what the distribution of, say, subsidies or positive productivity shocks funded by the government would have to be in order to completely neutralize that uncertainty shock, right? But clearly that's costly, and it would mean that people are placed in situations where, in absence of that government intervention, they would not be. Right? But I can solve numerically for that vector of, you might call it subsidies or whatever. The subsidies would have to be financed, of course, with something. Then I would have to introduce a tax instrument. I could use a lump sum tax or a proportional tax, whatever. But I could find out how big the tax would have to be and how I want to allocate it to completely neutralize the uncertainty shock. That's for sure. But of course, that's a costly strategy. Right? You could also say, okay, I can find out the economic cost other than through welfare that would neutralize this and design a tax program. And then please repeat your second question.
The introduction of unemployment insurance.
Yes.
To cushion this extent of uncertainty, but maybe
So,
has the same mechanism.
to be honest with you, I didn't talk about it too much. So in the end of the day, you could, we didn't do it, right? So people don't disappear into unemployment here. We could have unemployment would be easy. Unemployment would be a region additional sector. So there would be one common sector everywhere that would be unemployed. We didn't do it because that would already, in order to finance some basic income level, that would already require us to have a tax rate there. And you know, to me, and maybe this was a bad choice, but anyway, to me, this was too distracting from the bare bone of where we contribute. Because the thing here is really designing an algorithm that allows you to do this when right now you couldn't. Right? The only thing you can do right now is really use perturbation around steady state, around a perfect foresight path or whatever in continuous time. But this is completely novel. So nobody can do big shocks in discrete time space. So this is what we wanted to do. And for that, even the overlapping generations is immaterial, to be honest. So yeah, some people say, why do you have overlapping generations? Yeah, true. But on the other hand, I have these French workers and there I see that this is different. But yeah, I agree. This is just a little bit of a distraction in the end of the day, but the beef is really in solving this forward-looking uncertainty, discrete time-space model. Yeah.
So there are no further questions. Thank you very much.